Hello, this is a review of lecture number 1 from Chem 105. So, the first question is, what is chemistry? Well, chemistry is the study of matter. What exactly is matter? Well, matter is defined to be anything with volume and mass and is comprised of atoms. So, anything from a table has atoms, a house is made of atoms, everything on Earth that has volume and mass and contains atoms is considered to be matter. So we can divide matter into several subcategories. One of those subcategories is a pure substance. So notice that a pure substance has only one type of element or compound. The other type of subcategory that we divide matter in is called a mixture. And remember that a mixture has multiple types of elements or compounds in them. If it's a pure substance, we can further subdivide pure substances into elements and compounds. And an element is a single indivisible collection of protons and with neutrons on the periodic table, whereas a compound has multiple elements mixed together. A mixture, on the other hand, can be further subdivided into homogeneous and heterogeneous substances. The difference between these is the consistency. If you look at a mixture and it appears to be consistent throughout, then that is a homogeneous mixture. But if there are clear visible differences in the substance, then that is considered to be a heterogeneous mixture. Chemical reactions. What is a chemical reaction? So a chemical reaction is when chemical bonds break, form, or rearrange. A physical change, on the other hand, does not change at the atomic level. So something like bending a piece of metal is a physical change because while the metal is bent, none of the chemical bonds are broken, form, or rearranged when you bend a metal. So physical properties can be divided into intensive and extensive properties. Intensive properties are properties that are independent of quantity. These include things like smell, color, density, electrical conductivity, and solubility. So notice that all of these qualities are independent of quantity. So let's say if we have a bar of gold versus a few specks of gold, it doesn't matter how much, it's going to have the same color, it's going to have the same smell and density, and it's going to have the same electrical conductivity regardless of if we have a lot of gold or a little bit of gold. And that same is true for every compound. Extensive properties, on the other hand, are dependent on the quantity, and these include things such as length, width, mass, and volume. So, regardless of the element or compound or mixture or whatever type of matter we have, the more of it that we have, these extensive properties will increase. The length will increase, the width will increase, the mass will increase, and so will the volume. There are 3 states of matter for the purposes of this class. There is a solid, a liquid, and a gas. Notice that the solid, this red blob over here, has a definite volume and a definite shape in volume and mass. If we place it in the container, it does not take the shape of the container that we place it in. It stays the same. A liquid, on the other hand, does not have a definite volume, meaning that if we put a liquid in a container, it will simply change itself to fit the container. But it does have a definite volume, meaning that it will only fill up the container a certain amount. Gases, the third state of matter, does not have a definite volume, meaning just like a liquid, but unlike a liquid, it will expand to fill its entire container. So it doesn't have a definite density. Its density and volume changes according to its container. So, again, with solids, liquids, and gases, you can tell which one is which by the distance of the particles away from each other. Imagine that these red dots are particles, and in a solid, the particles are very, very close to each other, and they cling tightly to each other. Within a liquid, the particles are slightly more spread out, and see there's a little bit more distance in between them. And a gas, on the other hand, the particles tend to be very far apart from each other. They bounce around and repel each other, and they're free to flow just in any direction away from each other. So changes in state. So here I have all the changes listed. If we start with a solid and the solid turns into a liquid, that is called a melting change in state. If we have a liquid and the liquid goes to a solid, that is called a freezing change of state. Maybe instead of liquid and solid, it might be easier to think of it as water. So if we have like an ice cube that melts, the ice cube turns into water, that's melting. Or if we have water that turns into an ice, that's just freezing. Vaporization is when a liquid turns into a gas. In the case of water, if you're in your kitchen and you're boiling water, that liquid is turning into steam. It's vaporizing. That's the process of vaporization. These last few are not as common, but if we have a gas, or not, the words aren't as commonly used. But if we have a gas that turns into a liquid, it gets compressed or cools, and it turns into a liquid, then that's called condensation. And these last two, if you have a solid that skips the liquid phase and goes straight into a gas, that is called sublimation. A good example of this is with dry ice. If you've ever played with dry ice before, dry ice is called, it has that name because it sublimates. It looks like a normal piece of ice, and it skips the liquid stage and goes directly into a gas stage. So yeah, that process is called sublimation. The last change in state is called deposition, and that is when a gas turns into a solid. So again, it's sublimation and deposition skip the liquid phase when a solid goes straight to a gas, and then a gas goes straight to a solid. So these are something to memorize. Energy. So energy is defined to be the ability to do work. There are three types of energy, and there are only three. The first is potential energy, the second is kinetic energy, and the third is radiant energy. So potential energy is defined to be energy that is stored in somehow. So examples of this might be a battery. A battery has a electrons compressed together, and that's stored in the form of potential energy. Another example might be if you take a ball that's on the ground and you lift it in the air, that distance above the ground gives it potential energy, because you could let go and the ball could release its energy. Another example, maybe more applicable to this class in Chem 105, is chemical energy. Right, so maybe if you eat food, the food that you eat has potential energy stored inside of it in the form of chemical bonds. And when you eat that food, it breaks those bonds apart and releases that energy, releases that stored potential energy. The second type of energy that we'll talk about is kinetic energy. So kinetic energy is anytime matter is moving. So the energy of motion, moving from point A to point B. So some examples of this may be thermal energy, like heat, for example, is a type of kinetic energy. If you just think to yourself, really, what is heat? Well, at a subatomic, or at the atomic level, heat really is just the average speed at which the molecules move. So if they move faster, then that's just defined to be more, that's by definition that is just hotter. So, and then the faster that those atoms are moving, the more kinetic energy they'll have and the more heat that you'll feel. So another example of kinetic energy may be if you're playing baseball and you throw a baseball. The baseball as a projectile is moving through the air. It has kinetic energy because it's moving. And let's see, the third type of energy is, we'll call it radiant energy, or energy stored in the form of light, or in a photon. So an example of this may be the sun, right? The sun expels radiant energy in the form of its sunbeams, and that energy comes and hits the earth, and plants can absorb that radiant energy. Solar panels are also capable of absorbing that radiant energy. So there's only 3 types of energies. Any type you can think of will fall into one of these 3 categories. Okay, let's talk about some laws. So first we'll start off with the law of conservation of energy. The law of conservation of energy states that energy can neither be created nor destroyed. So a French scientist, Lesuvier, burned things in a closed container and observed that the mass did not change. This disproved the existence of phlogiston. So before this, people thought that maybe if you took wood, for example, and you burned it, that whatever was made up the wood would just simply disappear, or it was simply just destroyed. Because we now know that the burning of wood is an example of a chemical reaction, that the atoms in the wood don't simply disappear, but rather they combine with the air, or they turn into a gaseous stage, or they maybe turn into flakes, but they don't, whatever happens, they don't disappear or become destroyed. They just change form, perhaps combine with other atoms around them, and but they're still in existence. Phlogiston was the idea that that's what made things burn, that flammable materials had this substance in them that's called phlogiston, that we couldn't really measure it or quantify it, but that's what gave flammable things that burnable property. So something like oil had a lot of phlogiston, or maybe clothing or wood. But Lesuvier was able to disprove this idea and saying that, no, I think that that's not true. Let's see, the law of conservation of mass. No, so mass cannot be created nor destroyed. So then there's the law of definite proportions. So every chemical, which states that every chemical compound contains a fixed number of proportions of its elements. This was discovered by a scientist named Joseph Proust, and he said that you can add 1 or 2 atoms, but not 1.5, for example. At the time of this discovery, the idea of atoms weren't known yet, but Joseph Proust noticed that he was able to add certain proportions of mass to compounds, and these proportions were fixed, discrete to each other. Maybe, for example, if a compound had 20% silver in it, he could change it so it had 30 or 40% silver, but he couldn't make 25, for example. Now, with the knowledge of atoms, we know that whether adding a silver atom or 2 silver atoms is what's is the difference between those 2 compounds. And you can't add a half an atom, but you can add whole discrete numbers of atoms. And then we have the law of multiple proportions. So a compound forms from its elements through the... Oh, I didn't finish. That must be a typo. So anyway, this law was discovered by John Dalton, and he stated that combinations of atoms of unlike elements in small whole number ratios. And this proved that the evidence of atoms. It's easy to confuse these two, the law of definite proportions and multiple proportions. So I just want to review them one more time. So the law of definite proportions says that I want to emphasize there's fixed proportions. You can add fixed whole number proportions to atoms. You can add discrete amounts of atoms to compounds. The law of multiple proportions, on the other hand, states that compounds form from elements in small whole number ratios. This word small is just relative, I guess, because there's some protein compounds that contain hundreds and hundreds of carbon atoms long, but the general idea still holds true. But this is how we know the difference between carbon monoxide and carbon dioxide. For example, there's a CO versus C2O. It's that extra atom, or the small whole number ratio that's added to that compound. Again, these are really easy to mix up because they're very, very similar to each other. So, how exactly do we represent these atoms? Well, there's a variety of ways. There's a variety of formulas and models that we use to represent atoms. The first one is the molecular formula. And here's the example of C3H6O. This is probably one of the most common forms we'll see in Chem 105. And this is known as the molecular formula. And it just gives a very clear description of the number of each element in a compound. But it doesn't tell you that much about the actual structure. I mean, for example, where exactly are the carbon atoms relative to the hydrogens and the oxygens? And it turns out there's a variety of different solutions to that. So that's when structural formations come in, and these are actually drawn out. If you actually draw out, just explicitly draw where the carbon is, where the hydrogen is, and the bonds between them, Then for extremely large compounds, this can get very tedious, so it's easier to use a condensed structural formula, which is a mix between the previous two. There's also the ball and stick models that you typically see with chemists. They have just balls that represent atoms and just sticks you can stick in the balls and connect them together to represent bonds between those elements. It's not a very realistic representation of what's going on at the atomic level, but it's a very intuitive way, an interactive way to model a particular compound. And then finally, we have space-filling models. This is one of the more accurate ways to represent, because it's a depiction that just describes more accurately what is going on, as opposed to the ball and stick models. Okay, finally we have the scientific method. We use the scientific method to determine in science how we conclude that something is true. And so let's just go through the steps. The first step in the scientific method is observing something. So if you just make an observation, it could be something like when ice melts, it turns into water, and when water freezes, it turns into ice. So so that's an example of an observation, just observing something in the real world. The second step in the scientific method is forming a hypothesis. And the hypothesis is just a guess about how it works. So you could say something like, oh, I think that water and ice are actually made of the same material. They're just in different forms, right? Or I could say that maybe the ice or the water combines with the air around it to form the solid structure, right? Or whatever it is, whatever your hypothesis is, it's a guess on explaining how the observation in step 1 works. It could be right or wrong, but that's when step 3 comes in. Step 3 of the scientific method is forming a hypothesis to determine whether or not, or form an experiment to determine whether or not your hypothesis was correct or not. And then you repeat the process, and then you observe something similar, you make another hypothesis about how it works, and then form another experiment on that. Once enough people have performed the experiment enough times, or enough experiments have been performed explaining a certain observation, then it becomes a theory. And theories are more grounded and generally accepted as true. This definition of theory is quite a bit different from the English vernacular theory. Like you might hear a friend say, "Oh, I have a theory about what went wrong," meaning that, "Oh, I have a guess went wrong." The theory in this context means something very different. You could say something like the theory of evolution or germ theory, or things that there's so much evidence for them that they're so grounded, or there's so much evidence and proof and from the experiments that have been performed that they're generally accepted as true. A scientific law, on the other hand, is a summary of accepted facts of nature, or it's a summary of something that is observed. So, for example, Newton's 3 laws of motion, those are things that are simply observed in nature. And the last one is a scientific theory. Oh, I already explained this, but It's a well-tested explanation of why a natural phenomenon is observed or why a scientific theory is true.